I want you to try a little thought experiment with me for a second.
Oh, starting right off with a thought experiment. I like it.
Yeah, let's just jump right in. So picture a really high-end jewelry store. You know the kind, right?
The ones with really thick carpets and the armed guards standing at the door.
Exactly. Soft lighting, completely quiet. And you're looking through this immaculate glass display case at a stunning deep red ruby ring.
Okay, I can picture it.
And right next to it, resting on its own little velvet cushion, is a brilliant ocean blue sapphire pendant.
Two of the big three precious gemstones.
Right. And to the naked eye, to anyone just admiring the sparkle and the artistry of the cut, they look like two completely different dazzling stones. They seem to belong to totally different families of the mineral kingdom.
Which is exactly what most people think when they look at them.
But what if I told you that those two gemstones are fundamentally the exact same material? That they were both born from the exact same violent, high-pressure geological cookers deep inside the Earth?
It is a pretty wild realization.
And even more mind-blowing, what if I told you that the exact same material making up those million-dollar jewels is, right this very second, sitting in your pocket, making the screen of your smartphone actually function?
The line between a royal crown jewel and, well, a basic industrial component is incredibly thin. It's almost imperceptible when you get down to the atomic level. Welcome to our deep dive.
Today, our mission is to explore the staggering science, the rich history, and the massive modern industry behind corundum.
Right, corundum. That is the overarching mineral family that gives us both rubies and sapphires.
We are using a massive, comprehensive geological review today. It details the world's ruby deposits, classifying everything from their chemical makeup to how they formed billions of years ago.
And alongside that, we have an encyclopedic breakdown of sapphires, exploring their color spectrums, their mining history, and how human beings eventually figured out how to replicate them in high-tech laboratories.
So by the end of this deep dive, you won't just look at a gemstone and see a pretty rock. You're going to see a window into deep Earth history, a marvel of quantum physics, and honestly, one of the unsung heroes of modern technology.
We are talking about a mineral that has driven kings to madness, inspired ancient legends across multiple continents, and now it literally sits at the absolute heart of our global digital infrastructure.
Which is just crazy to think about.
It is. But to understand how a single material can possess that kind of historical and technological duality, we really have to start by stripping away the romance.
Okay.
We need to look at the raw chemistry, the internal architecture.
Okay, let's unpack this. If I put one of these stones under an incredibly powerful microscope, past the polished facets and the shiny exterior, what am I actually looking at? Like, what is the fundamental building block of this material?
You are looking at aluminum oxide.
Aluminum oxide.
Exactly. Chemically, it's represented as Al2O3. So that's 2 aluminum atoms bound to 3 oxygen atoms. That is the baseline composition of corundum. But the chemical formula only tells a fraction of the story, the true defining characteristic of corundum. The reason it actually survives billions of years of geological turmoil, and the reason it scores a 9 on the Mohs hardness scale, is its crystal structure.
It's a 9. Wow.
Yes, it is a masterclass in spatial efficiency.
Because I know these stones are notoriously tough, sitting right behind moissanite, which is at 9.5, and diamond at a 10. But how does just aluminum and oxygen create something that can scratch almost any other substance on Earth?
Well, that toughness is a direct result of how tightly those atoms are packed together in what we call a trigonal crystal system.
A trigonal crystal system.
Right. Imagine a massive collection of oxygen atoms. Now, picture them packing together as closely as physically possible in a hexagonal arrangement.
Like stacking spheres.
Yes, exactly like stacking spheres. If you take a layer of spheres and then you place the next layer of spheres into the natural depressions of the first layer.
Oh, I see. They lock in.
They do. You get a repeating, incredibly dense pattern. In geology and chemistry, this is known as hexagonal close packing.
Okay, so the oxygen atoms are forming this super dense scaffolding. Where does the aluminum fit into this tight arrangement? Because you said it's packed as closely as physically possible.
That's the key. Because the oxygen spheres are packed so densely, the empty spaces left between them are minuscule. We call these tiny voids octahedral sites.
Octahedral sites, got it.
The aluminum atoms are significantly smaller than the oxygen atoms, so they slip right into these voids. But nature is highly specific here. The aluminum atoms don't just fill every single available gap.
They don't.
No, they occupy exactly 2/3 of those octahedral sites.
Huh. Why two-thirds?
This specific ratio creates a framework where every single aluminum atom is coordinated by 6 surrounding oxygen atoms, 3 from the layer above and 3 from the layer below.
Oh, wow, so it's completely locked in from all sides.
Exactly. The resulting atomic bonds are phenomenally strong. It forms a locked-in, dense lattice that requires an immense amount of physical force or thermal energy to break apart.
And for me, the craziest part about that perfectly locked-in lattice is its default visual state. Because in its absolute purest form, this unbreakable crystal is completely colorless.
Completely transparent.
Right. It looks essentially like a very heavy piece of glass. It only becomes a precious gemstone when that perfect internal geometry is somehow compromised by outside elements.
Yes, and geologists refer to these outside elements as trace elemental impurities, or more technically, chromophores.
Chromophores.
Right. During the violent high-heat formation of the crystal deep underground, the surrounding environment is a chaotic soup of different minerals and fluids. It's not a clean laboratory.
It's just a mess of magma and rock.
Exactly. So occasionally, a rogue atom of completely different element manages to infiltrate the lattice and steal an aluminum atom spot in one of those tiny octahedral sites we talked about.
Okay, so I like to think of pure corundum like a blank canvas, or like a massive batch of plain vanilla ice cream.
Vanilla ice cream works perfectly.
Right, it has a solid foundation, but it lacks a distinct visual identity. If you take a tiny drop of specialized food coloring and mix it into the ice cream, you completely alter how the outside world perceives it.
That is a great analogy.
In the world of corundum, the identity shift is entirely dependent on which specific element crashes the party, right?
Exactly. If an atom of chromium, specifically the chromium 3+ ion, infiltrates the lattice and takes an aluminum spot, the entire stone turns red.
And boom, that colorless crystal instantly becomes a ruby.
It does. And the required concentrations are staggering in their efficiency.
Mm-hmm.
To generate a rich, vibrant ruby color, you might only need between 0.1% and 3% chromium oxide replacing the aluminum.
Wait, so the crystal remains 97 to 99% pure aluminum oxide?
Yes, the vast majority of the stone is completely unchanged. But if chromium isn't present in the surrounding geological fluids when the crystal forms, the stone takes a different path.
So what happens then?
If a tiny bit of titanium and a tiny bit of iron manage to sneak into those octahedral spots together, the stone turns blue.
And you have a sapphire.
You have a sapphire.
And the numbers on this are just wild to me. Just 0.01% of titanium and iron is enough to turn the entire stone blue. 1/100th of a percent.
It takes almost nothing.
Nature just sprinkles a microscopic dusting of trace elements into the exact same structural lattice, and in doing so creates two completely different cultural phenomenons.
Culturally, they couldn't be more distinct.
Yeah, and looking at the history of these stones, human valuation was heavily, heavily skewed toward the red sibling.
Oh, absolutely.
Yeah.
For centuries, the ruby was universally considered the absolute pinnacle of gemstones. It held a status that even diamonds struggled to match until relatively modern diamond marketing campaigns took hold in the 20th century.
Let's look closer at that fiery red sibling, the queen of stones. Because the ancient nomenclature alone carries so much weight here. The overarching name corundum derives from the Sanskrit word kuranvinda,
Which translates rather unromantically to hard stone.
Yeah, not the most poetic, but rubies had a dedicated title. In Sanskrit, they were called Ratnaraj, the queen of precious stones. Ancient cultures were absolutely captivated by the idea that a stone could look like it was actually burning from the inside.
That association with internal fire is a recurring theme across classical antiquity. Around 400 BC, the Greco-Roman philosopher Theophrastus categorized the ruby alongside anthrax, which is the Greek word for coal.
Oh, because it looks like a glowing coal.
Precisely. And centuries later, Pliny the Elder referred to these red stones as carbunculus, translating to little coal in Latin, observing that they resembled glowing embers pulled fresh from a hearth.
It's so visceral.
It really is. The word ruby itself is actually a relatively modern invention. It emerged in European languages during the Middle Ages from the Latin ruber, which simply means red.
Which brings up one of the most entertaining multi-century blunders in recorded history.
Oh, the spinal mix-up.
Yes. Because before the 19th century, humans had a shockingly simplistic classification system for gemstones. It was entirely based on visual observation. If a stone was incredibly hard and it was red, They just called it a ruby.
They didn't have mass spectrometry. They didn't have an understanding of aluminum oxide crystal lattices.
Exactly. And because of this purely visual categorization, some of the most legendary lead-soaked rubies at the center of human empires aren't actually rubies at all.
The historical irony is profound here. Consider the Black Prince's ruby.
This one is famous.
It is. This is a massive, irregular cabochon, roughly the size of a chicken egg, set prominently in the front cross of the imperial state crown of the British crown jewels.
A chicken egg.
Right. Or consider the Timur ruby, another gargantuan red stone in the royal collection. This one actually has Arabic inscriptions of the various conquerors who owned it carved directly into its surface.
They literally carved their names into it.
They did. Monarchs launched military campaigns, they committed high treason, they bankrupted entire treasuries over these stones, fully believing them to be the ultimate manifestation of the ruby.
And they are, in fact, spanels.
They are spinels.
They spent centuries fighting over a completely different mineral. How does a mistake of that magnitude go unnoticed by the most powerful empires on Earth?
Well, spinels is a fascinating imposter. It is magnesium aluminum oxide. So it crystallizes in the cubic system, which is fundamentally different from corundum's trigonal system.
Okay, so different structure.
And it's also measurably softer, sitting at an 8 on the Mohs scale compared to the ruby's 9.
So they should have noticed a difference in hardness.
You'd think so. However, spunels frequently form in the exact same high-temperature geological environments as rubies. Furthermore, they are colored red by the exact same trace element chromium.
Oh, so they're literally dug out of the same dirt, colored by the same chemical.
Exactly. Ancient miners in places like the Badakhshan region of Central Asia would extract these brilliant red stones side by side with true rubies. To the naked eye, a high-quality red spinel is virtually indistinguishable from a ruby.
I can only imagine the sheer panic in the royal courts when the science finally caught up. Like when a French mineralogist named de Bourneau helped establish the modern, rigorous science of mineralogy in the 19th century.
He essentially had to break the news to the crown.
Right. He effectively informed the British royal family that the centerpiece of their imperial regalia, a stone supposedly worn by Henry V at the Battle of Agincourt, a stone that supposedly deflected a battle-axe blow to the king's head, was the mineral equivalent of a cubic zirconia relative to true corundum.
Well, spinel is much nicer than cubic zirconia. But yes, the revelation certainly shifted this scientific understanding. But by that point, the cultural momentum and the sheer historical provenance of the Black Prince's ruby far outweighed its chemical makeup.
Which is why we still refer to it as a ruby out of historical deference.
Exactly. But this distinction between historical romance and hard science highlights the staggering economics of actual red corundum today.
Yeah, when you look at the modern market for true certified rubies, the numbers are difficult to process.
They are astronomical.
Take the Sunrise Ruby, which is a breathtaking 25.59 carat stone that went to auction in 2015. It sold for $32.42 million.
Incredible.
That is over $1.2 million per carat. That makes it more highly valued by weight than an equivalent-sized, flawless, colorless diamond.
Easily.
So what specific physical properties drive a stone to command $1 million a carat?
The valuation of top-tier rubies relies on a very specific visual phenomenon known in the gem trade as the pigeon's blood standard.
Pigeon's blood. It's such an intense name.
The term itself is a traditional, somewhat visceral descriptor originating from Myanmar, formerly Burma. Myanmar has been the undisputed source of the world's finest rubies since 600 CE.
Wow, 600 CE.
Yes. But there is rigorous physics behind the pigeon's blood look. It is not merely about the depth or darkness of the red hue. It is about a phenomenon called fluorescence.
The stone doesn't just absorb light, it actively emits it. It genuinely glows.
Exactly. We established that the chromium ion is responsible for the red color. But chromium serves a dual purpose within the corundum lattice.
Okay, what does it do?
When chromium is exposed to ultraviolet light, it absorbs that high-energy UV radiation and re-emits it as lower-energy visible red light. It fluoresces.
And you don't need a special black light for this.
No, you don't need to be in a nightclub with a black light to witness this. The natural ultraviolet rays present in everyday sunlight are more than sufficient to trigger this reaction.
That is so cool.
A stone with strong fluorescence appears to have an internal, almost radioactive fire burning within its facets. It creates a vividness that masks areas of darkness within the cut, resulting in this mesmerizing low-tone intensity.
But nature rarely provides a perfect scenario without introducing a complication. because there is a rival element that can completely ruin this glowing effect.
Ah, yes. Iron. Iron is the great antagonist of the ruby world.
The villain of the story.
It really is. If iron manages to infiltrate the crystal lattice alongside the chromium, it acts as a dampener. Iron absorbs the energy that the chromium is attempting to emit, effectively quenching or killing the fluorescence.
So it just turns the light off.
Exactly. So the million-dollar question for any ruby entering the market is, what is the ratio of chromium to iron inside the crystal?
And the answer to that question is dictated entirely by the deep earth environment where the ruby formed millions of years ago.
Yes, which maps perfectly onto why the geographical origin of a gemstone is the single most critical factor in its valuation.
Right. Let's compare the two heavyweights of ruby production. You have the historic champion, Myanmar, specifically the legendary Mogok Stone Tract, and then you have the current undisputed champion of sheer volume, which is Mozambique.
Two completely different geological environments.
Exactly. The rubies from Myanmar formed in a host rock called marble.
Yes, and marble is a metamorphic rock that originates as limestone.
Like ancient seabeds.
Exactly.
Mhm.
Limestone is essentially the accumulated calcium carbonate from crushed seashells and marine organisms on ancient ocean floors. The critical factor here is that marble is an environment completely starved of iron.
Ah, no iron to quench the glow.
Right. When the Indian tectonic plate collided with the Eurasian plate millions of years ago, the immense heat and pressure baked those ancient limestones into marble. As the corundum crystals formed within this marble crucible, they readily absorbed the surrounding chromium, but there was virtually no iron available to corrupt them.
So they come out completely pure.
Basically, the result is a ruby with less than 0.1% iron oxide. These stones fluoresce fiercely. They define the Burma pigeon's blood-strong fluorescence standard.
Now let's cross the globe to East Africa, because in 2009, the Montepose mine was discovered in Mozambique, and it completely disrupted the global ruby trade.
It was a massive find.
But the geology under Mozambique is radically different from the pristine marbles of Myanmar.
It is. The Mozambique rubies formed within amphibolite. Amphibolite is a dense, dark, metamorphic rock that is inherently rich in iron.
Oh, they had no choice.
Exactly. During their formation, these corundum crystals acquired their necessary chromium, but they were also forced to absorb iron from their immediate surroundings, typically registering between 0.1% and 0.6% iron oxide.
Which is enough to ruin the glow.
It elevates the iron content enough to partially quench the UV fluorescence. They are still exceptionally beautiful gems, often featuring remarkable clarity, and laboratories will still classify the finest examples as Mozambique pigeon's blood fluorescent.
But it's just not the same.
Right. They lack the intense glowing saturation under natural sunlight that characterizes the marble-hosted stones from Myanmar.
It's amazing that we can trace it back like that. And the geological mapping of these trace elements has allowed scientists to categorize every ruby deposit on Earth.
Yes, our sources break down primary ruby deposits into 3 distinct types.
Let's go through them. Type I deposits are magmatic related, and the mechanics of this are wild to me.
They're very dramatic.
These are rubies that formed incredibly deep in the Earth's mantle, only to be violently transported to the surface by volcanic eruptions. They essentially hitch a ride in alkali basalts or kimberlite pipes.
Yeah, in type I deposits, the magma is not the creator, it is simply the elevator.
The elevator, I love that.
Rubies existed as xenocrysts, which just means foreign crystals deep underground. The ascending magma tore through these deep rock formations, captured the rubies, and carried them upward in a molten slurry before cooling on the surface.
That's incredible.
We see these dramatic magmatic deposits in regions like Madagascar or Thailand. Contrast that with type 2 deposits, which are metamorphic related.
So this is more of a slow bake.
Exactly. This is the slow baking process within the Earth's crust. This category encompasses the type IA marble-hosted rubies of Mogok we talked about, and the amphibolite-hosted rubies of Montepose. These require sustained, localized extreme pressure and temperature, generally associated with massive tectonic mountain-building events.
And then we also have type 3 deposits, the sedimentary or placer deposits. This is where the Earth basically performs the preliminary mining operations for us.
Nature doing the heavy lifting.
Right, because over the course of millions of years, towering mountain ranges are worn down by wind, rain, and glaciation. The host rock crumbles. But because rubies sit at a 9 on the Mohs scale, They survive the brutal tumbling and grinding as they are washed down rivers.
They just tumble along until they eventually concentrate in ancient gravel beds.
Which is huge historically, right?
Oh, the historical significance of Type 3 deposits cannot be overstated. For the vast majority of human history, miners possessed neither the explosives nor the heavy machinery required to carve into solid marble or dense amphibolite.
So they just pan for them in rivers.
Exactly. The entire ancient ruby trade relied upon discovering these placer deposits in river valleys. Even in the modern era, the massive economic viability of the Montepus operation in Mozambique, which is projected to yield an astounding 432 million carats over a 21-year lifespan, is heavily subsidized by their secondary colluvial deposits.
So nature has already eroded the rock for them.
Right, leaving the durable, high-quality rubies concentrated and ready for extraction in the soil.
And we are currently tracking down this durable mineral in the most hostile environments imaginable today. Take the Apollutic deposit in Greenland.
Oh, that's a fascinating one.
We are looking at rubies that formed in rocks 2.7 billion years ago, now being extracted from the freezing, desolate Arctic landscape. The resilience of Corundum is staggering.
It survives anything.
But all of this intricate geology, the ability to map trace elements down to the fraction of a percent, has fundamentally altered the psychology of the gem market. Modern laboratories like the GIA or the SSF utilize laser ablation and mass spectrometry to identify the exact plot of dirt a stone originated from.
It's forensic gemology at this point.
It really is. This technology has turned gem dealers into high-stakes antique dealers.
The comparison to antiques is highly accurate. Because top-tier rubies are nearly indestructible, a newly mined stone from Mozambique isn't just competing against the current year's yield. It is competing against historical stones extracted from Burma a century ago that are still circulating in the market.
That makes total sense.
So the laboratory origin report has ascended to a level of importance that frequently rivals the visual beauty of the stone itself. Collectors will pay astronomical premiums for the romance, the historical weight, and the precise geological fingerprint of a certified Kashmir or Myanmar stone, even if a recently mined stone from Madagascar looks virtually identical to the unaided eye. What's fascinating here is that as much as the market prizes absolute perfection and transparency, nature is rarely uniform.
Very true.
Sometimes the most sought-after corundum specimens among elite collectors are defined entirely by their imperfections. They are prized for the deliberate, visible interruptions in their crystal lattice.
The flaws make them malleable.
Exactly. The most striking example of this geological rebellion is the Trapiche ruby.
The Trapiche ruby, pronounced Trapiche.
Yes.
If you look at a cross-section of one of these stones, it defies every expectation of what a gemstone should look like. It resembles a tiny, intricate wheel with 6 perfect spokes radiating outward from a central hexagonal core.
It looks completely manufactured.
It does. The name is actually borrowed from the heavy, spoked wooden wheels traditionally used to crush sugarcane in South American agriculture, because the visual parallel is unmistakable. How does a rock grow perfectly symmetrical spokes?
The formation of a Trapiche ruby is essentially a geological freeze frame. It captures a crystal in a state of chaotic struggle. Our sources analyzed the crystal's ontogeny, its complete developmental life cycle from initial nucleation through its growth phases to its final alteration. A Trapiche ruby narrates a highly specific 3-stage history of wildly fluctuating conditions deep within the Earth's crust.
Walk us through that 3-stage narrative, like what triggers this chaotic growth?
Well, stage 1 is relatively mundane. The crystal begins its life forming a central core under calm, stable geological conditions. It builds a standard hexagonal shape through slow, methodical, layer-by-layer atomic growth.
Very normal so far.
But then, stage 2 initiates. A massive geological disruption occurs. Perhaps a sudden tectonic shift or a massive injection of new mineral-rich fluids into the rock fracture.
Oh, so things get crazy.
Very crazy. The driving force, which geologists define as the supersaturation of chemicals in the surrounding fluid, spikes dramatically. The crystal is suddenly overwhelmed with building materials and is forced to grow at an accelerated rate.
It's growing too fast.
Exactly. Instead of continuing its smooth layer-by-layer expansion, it shoots out a skeletal framework along its primary crystallographic axis. These rapid extensions form the 6 structural spokes, which we call sector boundaries.
Because it is forced to grow so rapidly, the lattice construction gets sloppy, right? It loses its selectivity.
Exactly the opposite of its usual pristine growth. This rapid, adhesive style expansion traps whatever happens to be in the immediate environment.
It just swallows everything up.
Yes. Our sources describe these sector boundaries as highly porous zones. As the skeletal spokes shoot outward, they engulf fluids, they trap gases like carbon dioxide and hydrogen sulfide, and they encapsulate multi-phase inclusions of liquid, vapor, and solid molten salts.
Oh, wow.
They even swallow other surrounding minerals whole, like dolomite and rutile. It is a messy, turbulent growth phase permanently recorded in the stone.
And then, just as suddenly as it started, the geological chaos subsides.
Stage 3 marks the return to stability. The supersaturation levels drop, the driving force normalizes, and the crystal resumes its slow, methodical growth. It carefully fills in the empty spatial gaps between those chaotic, included spokes.
So it's filling in the pizza slices.
The pizza slices. The final result is a breathtaking composite. 6 clear, vibrant red pizza slices of relatively pure ruby, permanently separated by 6 dark, heavily included spokes of trapped fluids and foreign minerals.
It is a testament to the dynamic, shifting nature of the deep earth. But trapezium rubies aren't the only instance where nature leverages inclusions to create an optical masterpiece. We have to examine asterism, the phenomenon of star sapphires and star rubies.
Oh, these are stunning.
Instead of solid structural spokes, these stones appear to hold a glowing, ethereal, 6-rayed star that floats magically just beneath the surface of the gem. It literally glides across the stone as you move it in the light.
Asterism is a brilliant optical illusion orchestrated by microscopic intersecting structures. When corundum forms in certain environments, the surrounding fluid is rich in titanium. As the crystal cools, this titanium dioxide crystallizes internally as the mineral rutile.
Rutile.
Right. These rutile formations manifest as incredibly thin microscopic needles, commonly referred to in the trade as silk. Crucially, these needles do not form randomly. They align themselves in strict accordance with the underlying hexagonal geometry of the corundum lattice.
Meaning they intersect perfectly.
They intersect one another at precise 60-degree angles.
Okay, so you have a microscopic 3-way intersection of titanium needles embedded all throughout the crystal. But if you facet the stone like a traditional diamond with those flat geometric planes, you ruin the illusion.
A faceted cut would scatter the light chaotically. You wouldn't see the star. To unlock the star, the lapidary must cut the stone and cabochon.
And cabochon.
This requires shaping the gem into a smooth, rounded, polished dome, ensuring that the flat base of the cabochon is perfectly parallel to the intersecting planes of the rutile needles.
So it's like a smooth little half sphere?
Right. When a singular source of overhead light, like the sun or a bright spotlight, strikes that polished dome, the light penetrates the stone and reflects off the elongated sides of those millions of microscopic needles.
Ah, I see.
The rounded dome of the cabochon acts as a focusing lens. It concentrates those myriad reflections into a sharp, brilliant, 6-rayed star that appears to hover above the physical surface of the gem.
That is just incredible. And in exceedingly rare circumstances, nature decides a 6-rayed star isn't quite enough and produces a 12-rayed star.
A 12-rayed star requires a remarkable geological coincidence. It occurs when the corundum crystal simultaneously traps 2 entirely different types of inclusions during its growth.
So rutile and something else?
Yes. If you have the standard rutile needles intersecting at their 60-degree angles, and simultaneously the stone encapsulates tiny flat platelets of hematite intersecting along their own specific crystallographic planes, the 2 separate optical networks superimpose.
Double the stars.
The result is a dazzling, complex 12-rayed star. The historical giants of the gem world, such as the Star of Adam, which is a staggering 1404-carat blue star sapphire unearthed in Sri Lanka, or the legendary Star of India, weighing over 563 carats, are pristine examples of this phenomena.
1,404 carats, that's huge.
It's massive, and the valuation of these colossal stones isn't strictly tied to their color saturation. It is driven by the sharpness, the centering of the star, and the semi-transparent glass body quality of the corundum that allows light to penetrate deeply and reflect back vividly.
It is a profound paradox that the very elements we typically classify as flaws like trapped gases, messy structural growth, foreign titanium needles, are the exact mechanisms that elevate these specific stones to priceless status.
It turns our idea of perfection on its head.
It really does. Now, we have spent a significant amount of time analyzing the red sibling, but let's shift our focus. Here's where it gets really interesting. Because the ruby, for all its historical prestige, is relatively one-dimensional in its coloration.
Very true.
The true chameleon of the mineral kingdom is the sapphire. Let's explore the sweeping color spectrum of this stone.
The general public almost exclusively associates the word sapphire with the color blue.
Right, blue sapphire.
While blue is undeniably the most commercially dominant variety, corundum is capable of forming in virtually every color of the visible spectrum. You can find vibrant yellow, vivid orange, deep green, brown, and violet.
Basically a rainbow?
The single limitation is semantic rather than chemical. Corundum cannot be classified as a red sapphire because red corundum is, by definition, ruby.
Ah, right. We already gave red a name.
Exactly. Every other point on the color wheel falls under the umbrella of fancy sapphires.
Let's begin with the iconic blue, because the physics dictating that blue color operate on a completely different mechanical principle than the ruby's red. With the ruby, the chromium atom sits relatively passively in the lattice, absorbing certain wavelengths and reflecting red.
Right, it's pretty static.
But a blue sapphire engages in this frenetic, continuous game of subatomic hot potato.
That is an excellent way to describe it. The scientific term for this subatomic game is intervalence charge transfer.
Intervalence charge transfer. Okay, break that down for us.
As we noted earlier, achieving a blue sapphire requires the simultaneous presence of both titanium and iron, substituting for aluminum in the lattice. When a titanium ion and an iron ion happen to occupy adjacent octahedral sites, their proximity creates a localized state of charge imbalance.
They're too close together.
Right. When photons of light enter the stone and strike this specific pairing, the introduced energy triggers a reaction. An electron literally jumps from the iron ion across the gap to the titanium ion and then instantly jumps back.
Just back and forth, back and forth.
Millions of times a second.
So the light energy is powering a continuous volley of an electron back and forth between two distinct trace elements.
Yes, and this continuous jumping action is not random. It requires a highly specific, quantized amount of energy to execute the leap. It just so happens that the energy required for this specific intervalence charge transfer corresponds exactly to the wavelength of yellow light.
Oh, so it eats the yellow light to fuel the jump.
Exactly. Therefore, as the electron jumps back and forth, the stone acts as a sponge, absorbing all the yellow light out of the visible spectrum passing through it. If you take standard white light and actively subtract the yellow wavelengths, the light that successfully exits the stone and reaches the human eye is the complementary color on the spectrum blue.
That is wild.
It is a highly dynamic, active quantum process, which explains why such an infinitesimally small concentration of titanium and iron, just 0.01%, can fundamentally alter the color of an entire crystal.
It is a quantum leap happening millions of times a second just to look pretty on a necklace.
Pretty much.
And because the deep earth is a swirling mix of various trace elements, sapphires can emerge from the dirt displaying staggering variations. Let's examine some of the rarest, most prized, fancy sapphires on the market. At the very top of that list is the Padparacha.
The Padparacha is often considered the holy grail by elite sapphire collectors.
It's a gorgeous name. What does it mean?
The nomenclature is derived from the Sanskrit term Padmaranga, which translates to the color of an aquatic lotus flower.
A lotus flower.
Beautiful. It is an incredibly delicate, specific hue, a light to medium-toned amalgamation of pink and orange. The classic visual analogy is a tropical sunset, where the pink clouds blend seamlessly into the orange horizon over the ocean.
Okay, I can see that.
Historically, these stones were exclusively sourced from the gem gravels of Sri Lanka, though modern exploration has uncovered deposits in Vietnam and parts of East Africa. A completely natural, unheated Padparacha exhibiting the perfect balance of pink and orange is exceptionally rare and commands prices that routinely eclipse high-quality blue sapphires.
Wow. Then we have the stones that refuse to settle on a single identity party sapphires. Why limit a gemstone to one color when the crystal can display 2 or 3 distinct zones simultaneously?
Party sapphires, frequently referred to as bicolor or polycolor sapphires, display sharp, distinct geographic zones of entirely different colors within a single, continuous crystal lattice.
That's like a striped stone.
Exactly. You might encounter a stone that is vibrant green on one end, transitioning sharply into a deep, rich blue on the other. This phenomenon occurs when the chemical composition of the fluid feeding the growing crystal changes drastically over the millennia of its formation.
The environment just shifted while it was growing.
Right. Australia is currently the most prolific source of these heavily zoned stones. While they may not align with the traditional, uniform aesthetics of mainstream commercial jewelry, they have a massive cult following among collectors because they serve as a stark, visual record of changing geological conditions.
It's basically a timeline you can wear.
Exactly. They are also highly prized because this distinct, sharp color zoning is incredibly difficult to replicate synthetically.
Speaking of stones with multiple identities, let's look at the ultimate parlor trick of the gemological world. Color change sapphires. This is often called the Alexandrite effect.
Oh, this is pure magic to watch.
You can examine one of these sapphires outdoors in the midday sun, and it presents as a crisp, vivid blue. You walk indoors, turn on a standard incandescent lamp, and right before your eyes, the stone shifts to a deep purple or reddish violet. It appears as though you swapped the stone entirely.
It really does.
What is happening inside the lattice to cause that shift?
The fascinating truth is that the stone itself is doing absolutely nothing differently.
Right.
The shift is an optical illusion dictated by the light source and the specific sensitivities of the human eye, a phenomenon called metamerism.
Metamerism.
These specific sapphires possess a highly unusual cocktail of trace elements, sometimes a precise mixture of chromium, iron, and titanium, or occasionally vanadium. This unique chemical blend creates a very specific absorption profile.
Okay.
The stone heavily absorbs light in the yellow region, but critically, it leaves two distinct windows of transmission wide open. It allows light in the blue-green spectrum to pass through, and it allows light in the red spectrum to pass through.
So the stone is constantly transmitting both blue and red light simultaneously.
Always.
The color we perceive is just a matter of which wavelength is dominant in the room.
Precisely. The perceived color depends entirely on the spectral power distribution of the light illuminating the gem. Natural daylight is highly balanced, but the human eye has evolved to be far more sensitive to green and blue wavelengths. Consequently, when viewed outdoors, the blue-green transmission window dominates our visual perception, and the stone looks blue.
Makes sense.
However, traditional incandescent light bulbs, or candlelight, have a spectral distribution that is heavily skewed toward the red and infrared end of the spectrum. They pump significantly more red energy into the stone. The balance of power shifts, the red transmission window overwhelms the blue, and your brain interprets the resulting light as purple or reddish violet.
That is so cool. The gemstone is essentially analyzing the light source and reporting the results back to your optic nerve.
That is exactly what it's doing.
That interaction perfectly illustrates that color is not an inherent static property of an object. It is an active collaboration between the object, the light source, and the biological observer.
A three-way partnership.
And just as we saw with rubies, the geographical origin of blue sapphires dictates massive fluctuations in market value. There are two primary locations that highlight this disparity. First, the mythological Kashmir sapphires.
The lore surrounding Kashmir sapphires is unparalleled. They were discovered in the late 19th century, exposed by a landslide high in the remote, snow-capped Himalayas in the Padar Valley of India.
Talk about a dramatic entrance.
Right. The mining conditions were brutal, and the period of peak production was incredibly brief, lasting only a few decades before the primary deposits were largely exhausted. But the stones extracted during that narrow window are considered the absolute zenith of blue corundum.
Why? What makes them so special?
They possess a superior, highly saturated, vivid blue hue, combined with a microscopic dispersion of minute inclusions that scatters light internally. The trade refers to this sleepy, mesmerizing appearance as blue velvet.
Blue velvet. That sounds expensive.
It is very expensive.
Crucially, they maintain their intense color under any lighting condition, right? They don't turn dark, gray, or inky when you take them out of the sunlight, which is a common flaw in lesser sapphires.
Exactly. They hold their color perfectly.
This perfect storm of rarity, historical romance, and optical superiority is why they dominate auction records. Sotheby's recently sold a cashmere sapphire ring that broke down to an astonishing $242,000 per carat.
Staggering numbers. But on the complete opposite end of the spectrum, both in terms of geography and the sheer mechanics of their formation, you have the Yogo sapphires. Mined in the United States at Yogo Gulch in Montana.
Montana.
Yes, Yogo sapphires are geological anomalies. They are extracted from a lamprifier dike, and uniquely, they emerge from the earth displaying a flawless, uniform cornflower blue.
Right out of the dirt.
Right out of the dirt. They are virtually devoid of the rutile silk and heavy inclusions that plague sapphires from other global regions. Because they boast such high uniform clarity and color naturally, they're one of the only sapphire deposits in the world that never require artificial heat treatment.
That's incredible.
However, nature balanced this perfection with a severe limitation in size. The rough crystals are distinctively flat and wafer-like. Finding a faceted Yogo sapphire exceeding a single carat is an exceedingly rare event, making large specimens highly coveted by American collectors.
That detail about the Yogo sapphires not needing heat treatment is the perfect transition. Because for the vast majority of the global corundum supply, perfection does not come out of the ground.
If we connect this to the bigger picture, we see that human beings have never been content to simply accept the raw materials nature provides. When the earth yields a stone that is slightly too cloudy or a color that is slightly too pale, human ingenuity steps in to correct the geological oversight.
We just can't leave it
We
alone.
really can't. The intervention of the hand of man is arguably the most economically and technologically impactful chapter in the Corundum narrative.
Let's delve into the world of gemstone treatments. It is a known fact in the industry that the overwhelming majority of commercial sapphires and rubies available today have been artificially treated to improve their appearance. And this isn't a modern deception spawned by the Industrial Revolution. Humans have been artificially enhancing corundum since the days of the Roman Empire.
The ancients were surprisingly adept at this. Roman jewelers realized that packing certain dull stones in charcoal and subjecting them to the heat of a rudimentary blowpipe could occasionally improve their clarity.
Just a guy with a blowpipe and some charcoal.
Exactly. But what began as a crude trial-and-error process evolved into a highly exact, high-tech science in the modern era, heavily localized in cutting centers like Thailand during the 1980s and 90s. Today, technicians utilize specialized computer-controlled atmospheric furnaces to bake sapphires at temperatures reaching up to 1800 degrees Celsius.
Let's contextualize 1800 degrees Celsius. That is nearly 3300 degrees Fahrenheit. That is hot enough to melt iron, steel, and titanium.
It is infernal heat.
What physical metamorphosis occurs inside the crystal lattice when you subject a rock to that level of thermal trauma?
The primary target of heat treatment is the silk we discussed earlier, the microscopic needles of titanium dioxide, or rutile, that cause asterism.
Right, the star effect.
In a star sapphire, that silk is arranged perfectly and is highly desirable. But in a standard faceted gem, an overabundance of randomly scattered silk makes the stone look cloudy, gray, and visually dead.
It just looks foggy.
When the sapphire is heated to 1800 degrees, the immense thermal energy forces those solid rutile needles to literally melt and dissolve back into the solid solution of the corundum lattice. The physical obstructions vanish, and a stone that entered the furnace looking like a cloudy piece of gravel emerges crystal clear.
But it doesn't just improve the clarity, it actively upgrades the color.
That is the secondary benefit of dissolving the rutile androl. The titanium that was locked up within those needles is suddenly released and dispersed throughout the lattice.
Oh, and we need titanium for blue.
Exactly. Once liberated, this newly available titanium pairs up with existing iron ions within the stone, initiating the intervalence charge transfer, the quantum electron jump that we detailed earlier.
So they basically activate the hot potato game.
Yes. So through the application of extreme heat, a dull, cloudy, pale stone is transformed into a highly transparent, intensely saturated blue gem.
It is essentially putting the geological formation process on fast forward, giving the stone the heat it lacked deep underground. But eventually, technicians realized that simply rearranging the elements already trapped inside the stone wasn't enough. They wanted to introduce entirely new ingredients.
And this led to the controversial practice of lattice diffusion.
Lattice diffusion. This represents a significant escalation in human intervention. Instead of just melting what is already there, diffusion involves actively forcing new external trace elements deep into the crystal structure from the outside.
In the early 2000s, the global gem market was suddenly inundated with incredibly beautiful, perfectly colored pink-orange Padkaracha sapphires. The sheer volume was statistically impossible for natural production.
Right, because natural ones are so rare.
Exactly. Gemological laboratories were initially baffled until rigorous mass spectrometry revealed the deception. Unscrupulous dealers were taking vast quantities of cheap, pale, nearly colorless sapphires, packing them in crucibles filled with powdered beryllium, and blasting them with extreme heat.
Why beryllium specifically?
Because the beryllium atom is exceptionally small. Under the immense pressure of the furnace heat, these tiny beryllium atoms were able to penetrate the surface of the corundum and diffuse deep into the crystal lattice, fundamentally altering the color-producing chemistry from the outside in.
Sneaking right between the oxygen atoms.
Yes. It caused a massive crisis of confidence in the market until laboratories developed the necessary protocols to detect the beryllium signatures. But all of these treatments, heating, diffusion, are just half measures.
Right, because the ultimate human triumph over corundum didn't occur in a modern furnace. It happened in a French laboratory in 1902 when a chemist named Auguste Verneuil announced he had completely bypassed nature and successfully synthesized ruby crystals from scratch.
The invention of the Verneuil process, or flame fusion, was an absolute watershed moment in material science. Verneuil's apparatus was elegantly simple, but brutally effective.
How did it work?
He took highly purified alumina powder, finely ground aluminum oxide, mixed with a trace amount of chromium, and placed it in a hopper. This powder was then slowly sifted downward through an inverted blowpipe, producing a fiercely hot oxyhydrogen flame. As the microscopic particles of powder fell through the flame, they melted into tiny superheated droplets.
And these droplets fall onto a pedestal, slowly building up layer by layer.
Exactly. They fall into a rotating ceramic pedestal positioned beneath the flame. As the molten droplets accumulate, they slowly cool and crystallize into a single continuous lattice, building a teardrop-shaped crystal called a boulot.
A boule.
You can visualize it like a stalagmite slowly forming on the floor of a cave from dripping water, but occurring at thousands of degrees.
The end result is a crystal that is chemically, optically, and physically identical to a ruby mine from the Earth. But the Verneuil process has a violent concluding step due to thermal stress, right?
Oh, the thermal dynamics of the process are extreme. You have a crystal growing under a flame that is thousands of degrees, while the ambient air just inches away is at room temperature.
That's a huge difference.
This massive temperature gradient means the outer layers of the boule cool and contract faster than the inner core. The resulting internal strain is immense. If a lapidary attempted to cut the boule in that state, it would spontaneously shatter into 1,000 pieces.
So what do?
To relieve this pent-up thermal stress, the laboratory technician must take the completed boule, strike it sharply with a chisel, and split it perfectly in half longitudinally.
You literally have to hit it with a chisel.
You do. Despite this violent necessity, the Verneuil process allowed human civilization to mass-produce flawless synthetic rubies and sapphires for a fraction of the cost of mining.
But the demands of modern technology quickly outgrew the limitations of Verneuil's teardrop boules. Today, we aren't just synthesizing small gems for class rings and cheap jewelry. We are growing absolute monsters.
The scale of modern synthetic corundum production is difficult to comprehend. To meet industrial demands, scientists developed advanced techniques like the Czochralski process and the heat exchanger method, or HEM.
Yeah.
In these highly controlled environments, technicians melt massive quantities of raw aluminum oxide inside precious metal crucibles, typically constructed of iridium or molybdenum, to withstand the heat at sustained temperatures of 2,200 degrees Celsius inside a hard vacuum.
So no power at all.
Right. A tiny, perfectly structured seed crystal of sapphire is lowered into the molten lumina. Then, painstakingly, slowly, over a period of days or even weeks, the seed is pulled upward or the melt is cooled. The molten material crystallizes onto the seed, atom by perfect atom, maintaining an absolutely flawless lattice structure.
And how big do these get?
Utilizing these methods, facilities can now grow monolithic sapphire crystals weighing up to 200 kilograms. That is over 440 pounds of solid, structurally perfect corundum.
So, what does this all mean? Why is human civilization investing staggering amounts of energy utilizing precious metal crucibles and high vacuum chambers to slowly grow 400-pound sapphires? We aren't carving them into giant statues.
No, we definitely aren't.
We are doing this because sapphire has proven itself to be an unparalleled supermaterial for high-tech applications.
We value natural sapphire in jewelry, primarily for its hardness and its brilliant transparency to visible light. But mechanical and optical engineers revere synthetic sapphire because its transparency extends far beyond the narrow sliver of the electromagnetic spectrum that the human eye can perceive.
Oh, really?
A pure synthetic sapphire window is highly transparent from the deep ultraviolet spectrum all the way through to the infrared spectrum. When you combine that massive optical bandwidth with a Mohs hardness of 9, making it virtually impervious to scratching by environmental hazards like sand or dirt, and an incredibly high melting point, you have engineered the ultimate protective window for sensitive instrumentation.
And this application isn't just restricted to multi-million-dollar scientific equipment. It interfaces directly with everyday life. Think about the self-checkout lane at the grocery store.
Oh, the scanner.
Right. Look down at the clear glass window protecting the barcode scanner. You and hundreds of other people every day are dragging tin cans, glass jars, and rough cardboard directly across that surface. If that window were made of standard silica glass, It would be opaque with deep scratches within a week, rendering the laser
It
useless.
would be ruined immediately.
That window survives years of daily abuse because it is a thin slice of synthetic sapphire.
And the applications scale up dramatically from there. Because of its immense structural strength and chemical inertness, engineers use thick sapphire viewports in high-pressure vacuum chambers used for dangerous scientific spectroscopy.
Wow.
In the military sector, thick panels of synthetic sapphire are laminated with specialized polymers and glass to create shatter-resistant transparent armor for ground vehicles. This provides superior protection at a fraction of the weight of traditional bulletproof glass.
Bulletproof sapphire.
Essentially, yes.
Hmm.
The advanced F-35 fighter jet utilizes large, faceted sapphire panels to protect the delicate sensors of its electro-optical targeting system, ensuring the infrared cameras have an unblemished, scratch-free view of the battlefield, even when flying through rain and dust at supersonic speeds.
The tech industry is constantly trying to leverage this durability, too. Apple famously initiated a massive venture to manufacture entire iPhone screens out of pure synthetic sapphire.
I remember that.
The goal was to create a phone that was fundamentally immune to keys or coins scratching it in your pocket. The initiative ultimately collapsed. Growing and machining sapphire on that scale proved too costly, and while it is incredibly hard, sapphire is also more brittle than engineered glass and prone to shattering if dropped flat.
Hardness doesn't always mean toughness.
Right. Despite that setback, Apple still utilizes synthetic sapphire for smaller, critical components like comparison lens covers to prevent optical degradation from scratches. But all of these physical applications pale in comparison to the single greatest technological contribution of synthetic sapphire. It is the hidden foundation of the lighting revolution. It is the reason the room you are sitting in is illuminated right now.
This is the unsung triumph of Corundum. To understand it, we must look at the semiconductor industry. To build advanced microchips and specific electronic components, engineers need a stable, non-conductive foundation and insulating substrate.
Like a base layer to build on.
Right. Wafers sliced from those massive 200-kilogram synthetic sapphire bowls provide the perfect atomic template. For decades, scientists struggled to create a functional blue light-emitting diode, or LED. We had red and green LEDs, but without blue, we could not combine the three to create pure, bright white LED light to replace inefficient incandescent bulbs.
We needed the blue.
The breakthrough, which eventually won the Nobel Prize, involved successfully growing microscopic layers of a complex semiconductor material called gallium nitride directly on top of these synthetic sapphire wafers.
On the sapphire.
The atomic structure of the sapphire provided the necessary scaffolding for the gallium nitride to crystallize and emit that elusive blue light. The entire modern transition to high-efficiency white LED lighting, which has fundamentally reduced global energy consumption, is built upon a literal foundation of synthetic corundum.
That is just incredible. From a dark, violently pressurized crucible deep within the Earth's crust 2.7 billion years ago, tumbling through freezing rivers in Greenland, to being fiercely guarded as the crown jewels of warring empires, to the glowing digital screen in your hand and the brilliant white LED light above your head today. The historical and technological journey of Corundum is absolutely staggering.
We have covered a tremendous expanse of territory today. We began by deconstructing the romance, stripping both rubies and sapphires down to their identical, unyielding chemical backbone of aluminum oxide.
The vanilla ice cream.
The vanilla ice cream. We explored how an infinitesimally small dusting of rogue elements, chromium for a fiery red, titanium and iron for a deep blue, dictates a visual distinction that has captivated human civilization for millennia.
And we ventured into the deep earth to understand how they are forged in iron-starved marbles and dense amphibolites, how they trap the chaotic fluids of their birth to form trapezius wheels and floating stars, and how microscopic geological mapping dictates their immense modern valuation.
And we traced how human ingenuity refused to be sidelined. We learned how to apply extreme thermal energy to melt away their flaws, how to aggressively diffuse new elements into their lattice, and eventually, how to replicate the slow work of geological time in a vacuum chamber.
Growing massive, flawless 400-pound chunks to build the armor, the sensors, and the lighting of our modern infrastructure. The next time you walk past a jewelry store and admire a ruby ring or a sapphire pendant, I hope you see far beyond a polished, pretty stone.
See the science.
Exactly. I hope you visualize the intervalence charge transfers, electrons jumping back and forth like a quantum hot potato. I hope you visualize the deep, crushing geological pressures of tectonic plates colliding over millions of years. And I hope you recognize that you are looking at the exact same unbreakable atomic lattice that is currently transmitting the laser in your grocery scanner and providing the foundation for the light illuminating your home.
It is a profound realization that the ornamental jewels we use to signify wealth and romance, and the utilitarian materials we rely upon for high-tech survival and global infrastructure, are fundamentally, atomically, one and the same.
Which leaves me with one final, slightly provocative thought for you to mull over as we conclude this deep dive. Today, human beings can synthesize a chemically and structurally flawless corundum crystal in a laboratory for just a few dollars. We possess the technology to mass produce a stone that is completely devoid of inclusions, perfectly saturated in color, and physically superior in every measurable metric to anything that comes out of the dirt.
It's perfect.
Yet the global market still places tens of millions of dollars of value on the natural stones. We pay an astronomical premium specifically because of their microscopic flaws, their uneven color zoning, and the ancient, dirty geological fluids permanently trapped inside them. It begs a fascinating philosophical question. In a modern world where our technology allows us to mass produce absolute, repeatable perfection for pennies, is true value actually found in the unique, unrepeatable imperfections of nature? Think about it. Until next time.